Okay, let's talk about the light bulbs for just a minute. Better yet, let's talk about the batteries for just a minute. Alright, Emma, Victoria. We kind of talked about the battery a little bit last time. We said there's what we call a positive terminal, there's what we call a negative terminal, and, well, what's inside the battery starts with C, what's pronounced K. What? Coil? No. Well, what letter comes after the C if it's going to sound like K? No, there's chemistry inside there, right? Like Alex reminded us of, there's chemistry that will happen when we start taking charges off the positive terminal and bring them to the negative terminal. There's chemistry that happens to kind of replenish those positive charges. So a battery is going to be a source of charge for us, but we need to be hooked up to both terminals of the battery if we're going to be able to allow charges to get from the higher energy terminal down to the lower energy terminal. So we definitely have to use both sides of the battery. So now let's talk about the light bulb. What's this outer part made out of? Glass. What's the purpose of the glass? What's the purpose of the... Stop. What's the purpose of the glass? Nobody knows? To encase it why? The purpose of the glass is we don't want oxygen inside here because what's this thing in the middle called? Filament, and the filament is HOT. Really hot. Really hot, like 3,000 Kelvin, maybe 2,000 Kelvin, like super, super hot. And if there's oxygen present, it's going to burn. If it burns, it's not going to work anymore, right? So the glass is actually just to keep oxygen out. We usually have like argon or something, some inert gas in there. It's not going to be a vacuum. So here's the filament, and we want electrons to go through the filament. It actually doesn't matter which way. For an incandescent bulb, you can have electrons go this way or that way. It makes zero difference. For something like an LED, a light-emitting diode, it actually does matter which direction you send the charges through. Alright, so let's look at the two ends of the filament. We have one end which has a green wire, and that green wire goes all the way down to the very bottom of the light bulb. And then the other side has a blue wire, and that goes to the side of the bottom. So we need to hook this up so that one terminal of the battery goes to the very bottom of the light bulb, and the other terminal of the battery goes somewhere on the side of the bottom of the light bulb. Yeah, if you actually have been polite and didn't do it while I was talking, go ahead and do it now. And if your light bulb truly is broken, you can yell at me. Has anybody still not got any light? Still didn't get anything? Alright, so let me show you with some better equipment, and then I'm happy to help with you. Alright, so I'm cheating. I have my light bulb in a holder. One of these goes to the side, one of these goes to the bottom, and then I have a second wire also. So hopefully, if this wire is going connected to the bottom of the bulb, and this other wire is connected to the side of the bulb, hopefully it works, but it doesn't. Well, that's kind of... Either my light bulb's dead or my battery's dead. So let's see yours. I think you're doing like the right stuff. You just take that from the bottom of the right against the battery. So yours worked? No! Kara, can you lend your bulb to these guys? Victoria, yours worked? Can you lend your bulb to these guys? Because I think it's your bulb. I think my bulb's broken. You can usually see if the filament's broken. It doesn't look so bad. Yeah, I don't think you can hear it. I thought. These were new batteries.
Yeah, well, that's why it doesn't work.
So it works now?
No, the battery says 2013.
Yeah, I'm still surprised. Emma, is yours working now? No? Try this one. They said theirs worked. Okay, if you try different batteries, I'm a little surprised. That would be the problem. But it's only 2014, like the battery's still fine. How can you figure that? That's the battery. So it's the battery. Should it was the battery?
Yeah,
It was the battery. Right. The two batteries that didn't work, let's throw them in the garbage. Mine still doesn't work. Oh. Bad wire. The battery that didn't work goes straight in the trash. I had a bad wire. That was my problem. Okay. So sorry, there's a little bit of difficulty. Yeah, some of the batteries are a little old. Probably should have been thrown out. So this was, at least in here, the first example of an electric circuit that we've built. And the only reason this is different from what we've looked at already is that we've had a little bit of moving charge already. Like if I charge up my metal water bottle, like yes, the charges will move and so they distribute themselves to minimize their energy, but then they stay there. When we build circuits, that's not true. We have a continuous flow of charges around our circuit. Alright, so we do have a couple of new terms, a couple of new variables, a couple of new names for things today. But so what we want to do over the course of our final 20 minutes here is be able to describe what conditions need to be met in order to have current flowing through a circuit, and then gain a little bit of familiarity with our final variables for the year, one of which is electric current. Alright, so electric current pretty much refers to the rate at which charge is flowing around the circuit. It's not a perfect definition, but it's not bad. Right, so if we have more charges, we'll have a larger current. If we have less charges, we have a pretty small current. All right, and we are going to get a tiny bit, not tiny, we are going to quantify this stuff. In fact, let's just do it right now. The symbol for electric current is a capital I. And it's measured in, well, according to what I'm saying here, it's equivalent to an amount of charge divided by an amount of time that the charge is flowing through. So what is charge measured in? Coulombs. And what is time measured in? Seconds. So current, would be a number of coulombs per second, but we have a nickname for that. What is it? Not ohms. That's the other one we're going to meet later today. I think we've heard it. Victoria, say it louder. Who? Farads. Oh, farad is a unit for capacitance, which was in chapter 21 and it skipped. Yeah? It is a capital A, because Laura did the chapter 22 homework already, so she actually worked with this thing. It's called the ampere. So current is measured in amperes. The symbol for that is a capital A. And sometimes we just hear amps. Right, so amps is like the slang version of amperes. Okay, so current is one of our new variables for today. It's our second to last variable of the year. And we only have current if we have an electric circuit that is allowing the current to flow. So what do we need for an electric circuit? We have to have a closed loop of conductors, right? We need some sort of power source. Maybe it's our battery. Right? So here's like our Energizer battery with the positive terminal up here and the negative terminal down here. And then we have to be connecting those two terminals with a pathway of conductors. All right? We have to allow charges to flow all the way from the one terminal to the other terminal. So a closed loop of conductors, we need a battery or something else that's going to apply a potential difference. If we have no potential difference, the charges aren't going to want to go from one place to another. They need to be minimizing their energy if they're going to move around at all. Now, our network of conductors in our first circuit was, I guess we had a wire, right? We had like an alligator clip with a wire. And then you also had the light bulb itself. Right? You had the light bulb itself and the filament. This is actually a slightly weird circuit because we were allowing the charge to leave the positive terminal. It's flowing through the wire. It's flowing down here. And then it actually goes back in the other direction a little bit before it goes back to the battery. But if your light bulb lit up, you did have a potential difference, and you had a closed path of conductors. For those of you that didn't have success, right? We said your battery was no good, right? So you didn't have enough of a potential difference across those two terminals to get enough charges to flow. You didn't have enough charges to make the light bulb give off light. You definitely had charges moving through your circuit, but not enough to make the light bulb light up. In my case, I didn't have a closed loop. My wire was broken. The one I tried to throw out was broken. So I just didn't have a closed loop. My battery was fine. All right, let me shut up for a minute. Questions right now about you guys had a current because you had batteries, which had a 1.5 volt potential difference. You had conductors connecting one side of the battery to the other, and you had your filament on that closed loop as well. And when charges moved through that filament, they made it give off light. Questions about that first circuit? Yeah, perfect.
I have a random question. What's the difference between a chargeable battery and a rechargeable?
What is the
I mean,
difference between a
a
battery you can
battery-
recharge and a battery you can't recharge? Yeah. I don't have a tremendous understanding of the chemistry that's going on inside here, but let me change your question a little bit. I got a new phone like 2 weeks ago, I think, and last time I got a new phone, the battery was okay. Like, I didn't have to charge it. I could go at least a full day without recharging my phone battery, but it didn't take too long before that was down to like maybe I had to charge it twice a day. The new phone I just got, I think I was able to get it 2 days before I had to recharge it, and I want to keep it that way as long as possible. You guys have heard that like batteries have like memory? Some of you have kind of heard that. That's sort of true. So I'm trying really hard right now to not recharge my phone until my battery's almost dead. Now my understanding of why that kind of works is that we already said there's chemistry going on inside this battery to provide that potential difference, right? So it's not like we just have two compartments in the battery and we have some charges in this one and some charges in that one, and the energy of these ones is less than the energy of those ones. That actually is true, but we don't have that total like separation. We just have like two holding tanks. We have chemistry that takes place to kind of keep that voltage, keep that electric potential difference, sorry, I used a bad word, going on. And eventually, like, the chemistry runs out. If we're out of reactants, right, we can't make more products if we're out of reactants. So we can recharge and force that chemistry in the other direction. It's like is that called a reversible reaction? What is that called?
I think a redox.
Yeah, well, it's definitely a redox, but a reaction that you can make go either way. Doesn't it have a name? Half of you are taking chemistry, so you need to remember that kind of stuff. All right, whatever. Part of that chemistry, at least my understanding of it, does have a solid within here. I was going to draw like a rectangle, but I'm sure it's more intricate than that. We have a solid that kind of dissolves, right? And then like forms someplace else. So maybe a different solid will form over here. When I recharge the battery, right, I'm going to be reforming this solid out of solution. If I start doing that when there's still a bunch of solid there, it's not going to attach. Like the new solid isn't going to attach so firmly. I don't like how this description is going. Sort of. Sort of. Let me just rephrase it to, I can form a better solid if I'm doing it all at once, not if I'm doing it piecemeal. Like I already have some here, and then I'm going to attach some to it here, and attach some to it here. The process works way better if we're not starting with some of that chemical solid already there. I know that wasn't a great explanation. That's as much as I know about it, and it is valid. So it's not memory. It's not like there's like it's not like there is computer memory in the battery, but there actually is some chemical memory. So sorry, I didn't have a great answer to that. So for a non-rechargeable battery, I think it's just a different chemistry that doesn't really allow for that very efficient. You actually can sort of recharge a non-rechargeable battery, it just doesn't work very well. And they have a tendency to kind of get super hot and sometimes they catch on fire and stuff. Alright, so when we draw circuits, and we're not going to get too in there, we're just going to skip this today actually. We are going to draw circuits, we're not going to do it today. So we already, and I think this is actually review for us as well. So we already mentioned that the rate at which charges are flowing is called electric current. We did say that the symbol for current is a capital I, and the unit for it is the ampere. We already said, and this is on your equation sheet, but we already said so, that current equals the amount of charge divided by how much time we allow those charges to flow. So back to our light bulbs. Right? There's not that many powers of light bulbs available. Right? I don't even know if you can still buy a 60-watt bulb. I think you can still buy 40-watt bulbs. I'm not so sure you can buy a 60-watt bulb. What does watts measure?
Voltage.
Bad word and wrong answer. One of those I could handle, not both. What do watts measure? Yeah, power. I heard it from one of you. I'd rather hear it from like 15 of you. So watts measure power, right? So these light bulbs are powerful, and I know we talked about this earlier in the year. And pretty clearly, a 60-watt bulb is more powerful than a 40-watt bulb. Right? So in your foursomes, I'd like you to decide how that more powerful bulb would look different from the less powerful bulb. Right? So take 20 seconds, and your foursomes have an answer for that. Okay, I think there's more than 20 seconds. Yeah, how's the 60-watt bulb going to look different? Brighter. I agree. I 100% agree. So power is, the rate at which work is done, but work is also the change in energy. So the light bulb is changing electrical energy into other types of energy. Like these light bulbs produce radiant energy, they also produce thermal energy, and they get very hot. These ones don't get so hot. The real ones get pretty hot. So a 60-watt bulb is converting electrical energy into other forms at a faster rate than the 40-watt bulb. So it's going to be brighter, it's going to be hotter too. Or at least it's going to get hot more quickly than the 40-watt bulb. Now, what are we plugging those light bulbs into? An outlet. And what's the potential difference of the outlet? We talked about this last time. We need to know this, right? 120 volts. So let me draw the bulbs. I mean, we'd have them in like a lamp socket, but so here's one bulb. We can call that the 60 watt bulb. Looks weird. That one looks less weird. 40 watt bulb. We're giving both of them 120 volt potential difference across the filament. Yet, different powers. Right? And it's different powers because it's a different amount of current, a different number of charges per unit time that's going through the filament. This 60 watt filament is going to have more charges, a larger current, than the 40 watt bulb. Less charges going through this one. And the way that we control how much current, if we can't do it with the potential difference, because we can't. We plug things into walls, 120 volts. There are things we could do about that, but that would have to be built into the thing that we're plugging in. We don't regulate that like externally. The way that we control that is by having different amounts of what we call electrical resistance internal to our light bulbs, or internal to whatever the heck we're using. All right, so this is our last variable of the year, I think. Exciting. And it's one of our three major electrical variables along with electric potential difference and current. Okay, so electrical resistance is a property just inherent to the material that the thing is made out of, which controls how easily charge can move through. Okay, so this is my PVC rod, and we said this is a good insulator. So this would have a resistance that makes it really difficult for charges to move through. Right? Insulators would have one extreme of a resistance, and then conductors, right, the aluminum edge of the whiteboard would have the other extreme of resistance. Right? So high resistance or a large value of resistance does mean that charges have a very hard time getting through the material. The resistance of this whole PVC pipe might be something like 500 million ohms. Ohms is the unit for resistance. That'll be up top here in a minute. The resistance of this whole metal border to the whiteboard might be 2 or 3 ohms. Right? So high resistance means very difficult time getting the charges through the material. There is a high resistance to the charges moving. Alright, so we do have a relationship between our three really important electricity variables. It's called Ohm's law. Gregor Ohm, I think. Gregory Ohm, one of those. Tells us that resistance is the ratio of the potential difference we apply to something over how much current will get moving through that thing as a result of the potential difference. And this is actually not true for all materials. It's true for some materials, but most of the materials we would use, at least over a low temperature range, pretty much obey Ohm's law. All right? So we can calculate resistance if we know the potential difference and the current, or if we know two of those things, we can calculate the other one. Makes no difference. And then we do have a nickname for the unit of resistance, and as I said before, that's ohms, O-H-M-S, and the symbol for that is the Greek letter omega. That makes sense. And it kind of looks like a horseshoe. It kind of looks like a horseshoe. All right, I saw some dirty looks, so let me pause and question me or yell at me. So I said a minute ago that not all materials obey this law. If they do, we actually call them ohmic materials. Ohmic materials should have a constant resistance at pretty much all temperatures. And I think we already addressed this, but if you can fill in the blank, conductors would have a relatively blank resistance. Take 10 seconds, see what word you think goes there. All right, what's a good word for that? We got a low resistance, right? right? The charges can flow through quite easily. Yeah. All right, we have like 7 minutes, so let's see some context for using Ohm's law. I definitely want to collect some data and use Ohm's law next class, so we'll probably lab for a pretty good chunk of next class. I know some of you are itching for another secondary assessment grade, so I'll have something you can hand in for that. And this time it will work, unlike the balloon lab. But let's see some context. So we have one of our 1.5 volt batteries, right? It's got 2 terminals that we connect with a wire, and that's it. And this is not something we want to do, right? We don't want to just connect the 2 terminals of the battery with a single wire, because the wire, well, what do you think? Good conductor or bad conductor? The whole point of the wire is to be a good conductor, right? So the wire is a very good conductor, and if we do just connect the 2 terminals, it actually could be dangerous. We could have so much current flowing through that wire that the wire will get super, super hot. That could be bad, and we're definitely going to kill the battery, right? If we take way too much charge, we're going to not allow that, the chemistry is going to exhaust itself in maintaining that difference in energy. So we would not want to do this, but we could. So how much current would go through the wire if we did do that? So if I want to do a diagram, right, I can just draw the battery. I haven't showed you how to draw the proper circuit diagrams yet. I can connect the 2 ends of the battery with a wire. I can identify my potential difference, delta V, and you have to use delta V. You cannot use V, that's wrong. Okay? Delta V is 1.5 volts. The resistance, our newest variable, is 1.8 ohms. And then we're looking for how much current. Right? We definitely will use Ohm's law here. We have to go with the assumption that the wire is ohmic. I can rearrange Ohm's law to isolate the current. And then my potential difference was 1.5, my resistance is 1.8. I think that's 0.83. Yeah. And 0.83 what? 0.83 amperes. I don't get as upset with amps as I do for voltage, but let's get it right. 0.83 amperes. Okay? We don't abbreviate meters and say meets, right? We would never do that. I don't know why we think we can do that for electricity variables. Questions on that first example? All right, let me have you guys do one on your own, right? So you'll be confident you can do the homework all on your own. So a heater has a resistance of 22 ohms, and we connect it to an electrical outlet, so not a battery, right? 420 volts. How much current will flow through the heater? So go ahead and finish that one up. I'm going to collect some of the stuff I handed out before. Victoria, you already did it? Yes. Yeah, I mean, I'd like for you to, yeah, just stay for like 90 seconds. All right, how much current? 5 point who? 5.5 amperes. Yeah, so hopefully you showed all your work, but ultimately we would be using Ohm's law and again solving for current, and we have our 120 volts, and what was the resistance? Oh great, so it makes my counter pop up, and then it gives me the color wheel of death, so I can, great, thank you. That's fine, whatever. I'm sorry, what was it?